You're hopefully familiar with the equation W equals Fd, work done equals force times distance. In this lesson video, we're going to apply this to A-level situations, which basically means we're going to change the distance to a displacement and we're going to try applying it at different angles. And then we'll also apply it to an expanding gas. Firstly, let's make sure we are defining things well. So I'm going to change the equation to W equals Fs. Work done equals force applied multiplied by the displacement in the direction of the force. Okay, so direction is extremely important here, and with F and S both being vectors, well, that's a handy reminder. We're multiplying two vectors, so work done, energy, is a scalar quantity with no direction. Let's put this to use. Here I have two ramps with two identical trolleys of mass 2 kilograms being pulled up them to a height of 0.45 meters. Which one is easiest? Which one requires the least work to pull it up the slope as shown? Commit yourself to an answer. Pause the video. Okay, now let's work it out. Hopefully you did this already because that's really going to help you to understand what's going on. So, ramp A is at 30 degrees from the horizontal. It has W equals 2g acting vertically down, T acting along the string, and N acting perpendicular to the ramp. I'm going to make my x-axis go along the ramp as this removes N from my calculations. So, the component of the weight acting down the slope is, let me draw my vector triangle. So it's 2g sine theta equals 9.81 newtons. And the distance travelled is 0.45 over sine 30 equals 0.9 meters. Giving us W equals 8.829 joules. Okay, too many sigma figures there, but let's just leave that for now. Now, for the 60-degree slope, here's the diagram. Weight down the slope is 2g sine 60. Displacement along the slope is 0.45 over sine 60. So the work done is 2g sine 60 times 0.45 over sine 60 equals 8.829 joules. It's the same. The work done is the same for both, but we know intuitively that a 30-degree slope is going to feel easier. The reason is simply that with a 30-degree slope, you need to apply less force for a longer distance. And applying less force is easier. Now we could have done that more simply. All the work done is being done against gravity. So that means the work done is simply the force applied multiplied by the vertical distance. So the force is weight, mg, since we need to overcome that. And the distance is 0.45 meters. So the work done equals 2g.45 equals 8.829 joules. Now that's a key part of this lesson, that calculating the work done, we need to only consider the displacement in the direction of the applied force. For a frictionless ramp, the force to overcome is only the force due to gravity, so only the vertical displacement is needed. In reality, there is going to be friction and the efficiency is going to change. We could easily calculate the efficiency of a ramp using a simple experiment. If you pull a trolley up a ramp using a Newton meter, so the force parallel to the ramp can be measured, and the displacement along the ramp can then be used to calculate the total work done. Now, if you calculate the work done against gravity using the weight of the trolley and the vertical displacement, since total work done equals work done against gravity plus work done against friction, we can now find the work done against friction. One step further, we can calculate the efficiency of the ramp using efficiency equals useful work done over total work done times 100%. And now that allows us to explain the whole system. That covers the core of work done and efficiency. Specifically, we need to be clear that when we're working out work done, that we're thinking about the force multiplied by the displacement in the direction of the force. In my next lesson video, I'm going to look specifically at what happens when we have a gas expanding.